This video will continue our discussion of finding absolute maxima, minima, extrema. I'm given another example. This area won't be a rectangular area. It won't be triangular. It won't have anything. It won't just straight edges. We're going to have a rounded edge in some sense here. So let's take a look at it. So first, let's figure out that region. So we have y equals x squared. So we know that is a parabola. There's my y equals x squared. And then we also have y equals 4, which is just going to be a flat line across there. Y equals 4. So we are talking about the absolute extrema that is located inside of this enclosed region here. So it can include the boundaries, it can include any of the sides or any of the inside. Okay, so first off, we'll try not the boundaries, we'll just do the calculus. So we find the partial of that function with respect to x. That's going to give me y minus 2x. The derivative with respect to y is going to give me x. Right? That's kind of nice. And then that's our system. So we get y minus 2x equals 0. We also get x equals 0. That's nice. Right? That actually answers our critical point question. X equals 0 has to satisfy both. So if x is 0, y is 0. So our critical point, our first one, is going to be 0, 0. Right? And then we'll do the function value here. If I plug in 0, 0, I get 0. Okay. So we have some boundaries here, but we only have two. I got this first boundary, and then we have y equals x squared, which is the underneath. Let's deal with the first boundary. The first boundary is, we get all the x's, and then we get y equals 4, and this is ran from, and we got to find where they intersect. So x squared is equal to 4 when we got plus or minus 2. So I know that this is ran from negative 2 to 2. So I do that same method that we saw in our last problem. Got f of x 4, and I plug in y is 4. So I get 4x minus x squared. Okay, so f of x is equal to that. I'm just rewriting for note's sake, and I know it's the interval negative 2 to 2. So we have to find the absolute extrema of that. I find my derivative. I got 4 minus 2x. We set that equal to 0. So x is equal to 2. So that adds some critical points there. So the next critical point would be the point x is 2. If x is 2 in this case, y is 4. So the function value of 2, 4, we'll figure that out. We also have to plug in negative 2 and 2. So negative 2, if I plug negative 2 in for that bound, the y is also 4. We'll have to figure out that function value as well. So that covers part 1 there. Let's do part 2 now. Okay, part 2 is going to be y equals x squared. So I'm going to plug that in as, okay, I get x, but y now is x squared. And I'm going to plug that into my function. So I got x times x squared minus x squared. So this new function here is going to be x cubed minus x squared. That is a new function of x on that line. So I take my derivative. And I got 3x squared minus 2x. I set it equal to 0. I'm going to solve now. Notice there's x in each one of these. So we get two values. Right? We have a product there. I get x equals 0 and x equals 2/3. All right, I already have x equals 0. The other point I'm going to need is x equals 2/3. How we get our y is from here. Y is x squared, so y is going to be 4/9. So I need to find the function value for that as well. All right, that covers everything. These four values are going to tell me which is the absolute max and which is going to be the absolute min. So we just got to think about plugging these in. So we have 2 times 4 minus 2 squared. That's going to be 8 minus 4, so we got a 4 there. Okay, I got negative 2 times 4 minus negative 2 squared. That's negative 8 minus 4, which is a negative 12. And then the last one that's not going to be the cleanest we got 2/3 times 4/9 minus 2/3 squared. That gets me 8/27 minus 4/9. All right, if I keep going with common denominator, sorry, I'm working weird down here. I got 8/27 minus 12/27, which is going to be a negative 4/27. So the last thing we can write, absolute max of 4 at 2, 4, absolute minimum of negative 12 at negative 2, 4. All right, so even if it's a weird shape, we usually can get through it just by using what it's called and plugging it in, just like we would have if it would have just been a line. All we have to do is recognize on that boundary what is what. These are pretty long. If they show up on a test, right, they may just not have very many sides, or maybe the algebra side of it is pretty straightforward, meaning I give you a nice pretty polynomial. You can imagine if we start throwing sines and cosines, stuff like that at these type of problems, the surfaces get really complicated. We also will have a bunch of max and mins, which will make the problem even more horrendous than the ones that came from this section.